Deformed Cannibals in the Hills horror show. Okay, so before we get started, I probably just need to cancel my office hours this afternoon because I'm supposed to attend 2 thesis defenses, one after the other, and it's going to go all afternoon. So I think that I just will probably not be available this afternoon. Sorry about that. So today we will start talking about communities in a bit more detail. We'll start sort of digging into what we think of as community structure. And community structure is generally thought of as the relationships among species and how they are organized. This is pretty complicated stuff, so we will try to keep it as simple as we possibly can. We will use very, very simple diagrams, and you'll see why in a minute, because if we use the real ones, I don't even understand those. So this is an example, though, of what we consider a food web. So a food web has what we think of as different trophic levels. So these trophic levels indicate how organisms make their living. So down here at the bottom we have diatoms, and they are photosynthetic. And for most food webs, you have plants at the base of the food web. And everything else in the food web eats the plants. So that's why it's structured like this, with plants at the bottom, because that's the base. And then you have organisms that eat the plants, and then you have organisms that eat the organisms that eat the plants. So by convention we call these herbivores, and by convention we call these carnivores. And with this food web you can see that we've got kind of a level in which we're equating all of these crazy species that are really different from one another. Well, they're on the same level because they make their living in the same way, and they share common resources at the lower level. So whales, these crab-eater seals, flying fish, penguins, and squid, they all eat the krill. So they are on the same trophic level. That means that they may compete with one another. So within a level, you may have competition. Between levels, you have exploitation. These guys are exploiting these guys. These guys are exploiting these guys. That means that these guys up here, they are exploiting some of the guys on this level. Okay, so Ross seals, Weddell seals, large fish, and emperor penguins all compete for these fish. Right? You can see that Ross seals and, well, no, let's just leave it at that. You have this kind of complicated structure here where leopard seals consume Ross seals, Weddell seals, and penguins. They don't eat fish. And so these guys consume these 3, but look, they also consume individuals from a lower trophic level. So this leopard seal is consuming 2 different trophic levels. The definition for that is an omnivore. Now we are used to thinking of omnivores as consumers that eat animals and that also eat plants. But that's not the ecological definition of an omnivore. An omnivore in ecology eats from 2 different trophic levels, regardless of which levels they are. So here you have a kind of a top predator eating 2 different kinds of animals. One that eats smaller animals and one that eats krill. This guy's an omnivore. The killer whale is also an omnivore. It kills blue whales, actually, and it also kills some of these larger animals and eats them. So killer whales are omnivores. Leopard seals are omnivores. So you have, even with a fairly simple food web, a fairly interesting and complicated structure. What you need to focus on is what the levels mean. The levels indicate that certain species make their living in the same kind of way. Here in this particular food web, we have photosynthesis. Here we have the consumption of plants. Here we have the consumption of these herbivores. So all these guys eat herbivores. They compete for these resources. So when you have multiple species within a single trophic level, they are competing. Exploitation, generally in our food webs it's predation, but I'll show you a parasitoid food web later. Exploitation is indicated by the vertical relationships. So notice that flying birds aren't really a part of this food web, except that they eat krill. Right? Nobody in this food web eats them. That's really interesting. That's kind of unusual, because mostly when we have food webs, everybody's connected to somebody else. Now this is an Antarctic food web. Okay. You know it's Antarctic because there are penguins in it, and there are no penguins in the Arctic. And it's a little bit unusual from the standpoint of most of our food webs, because when you think of terrestrial food webs, you think of individual plant species. And here we're just lumping all of the photosynthesizers into one category, diatoms. And we're not really seeming to care about which diatom species there are. Okay, this is kind of a preview of how ecology treats individual species as we move up the level of organization from individuals, that is adaptation, to populations, to species interactions, to communities. The individual species may become gradually less important as we start talking about communities and ecosystems. In ecosystems, they don't matter at all. We never talk about species. In community ecology, sometimes we will lump species together. So don't think that this is just one species in this case. This is a whole variety of diatom species. We're just not breaking them out. Okay? So this is how we conceive of food webs, and it gives you a snapshot of the basic organization. Each level makes its living in a different way. Species within a level compete. The relationships between levels indicate exploitation. Now, we're not going to try to deal with real food webs all that much. We will try to use selected food webs that are comprehensible. What we're going to do instead is illustrate food web principles using very simple ball and stick diagrams. Okay? And that's because real food webs, as you'll see in a second, can be challenging. So this is a typical, say, terrestrial food web. We might have 4 plant species here, and they might compete with each other. That's kind of not the point of food web organization, because we're interested in these links that link the levels more than we are about competition within a level. There is a sense in which competition within a level is very important to food webs, but we'll get to that. For now, we really want to focus on these vertical relationships because we haven't really had a way to consider those before. Now, why are we using ball and stick diagrams? Here you go. Okay, that's a real food web. Okay, please memorize that. There'll be an exam question on that. Yeah. So this is an actual food web. Okay, this is 10 fish species and their foods. 1, 2, 3, 4, 5, yeah, right, 10 fish species. Okay. And so, hey, let's simplify it. And we get this one. That's way better, right? That's way better. So that's why we don't do that. Food web ecologists spend a lot of time trying to just visualize interactions and trying to make sense of them. And when you're dealing with even a simple food web, and believe me, this one is simple, it can take a lot of your time and energy and computing power to really figure it out. So we're not going to use real food webs except very selectively. So let's go back to our ball and stick diagram and try to explore some of those things that we saw in the initial food web in a little more detail. So remember, by convention, we are going to talk about the base of the food web typically will be photosynthetic plants. And they are consumed by primary consumers or herbivores, and the herbivores are consumed by secondary consumers or predators. You can have tertiary consumers, you can have quaternary consumers, you can have quaternary consumers. You can have as many levels as you can think of. But there's a catch to that. For reasons that we'll go into, food webs that have many, many levels tend to be less stable. And they often collapse. So we find that for many food webs, you get 3 or 4 levels typically. You don't get that many food webs with 5 or 6 or 7. Think about it in these terms. Let's consider an African food web. So you have grass. You have zebras, right? The zebras are the primary consumers. They're the herbivores. They consume the grass. What consumes the zebras? Lions. Okay, well, who consumes the lions? Well, nobody. It's a 3-level trophic web. And that's because, number one, there aren't that many lions, and you can't support a population of super predators. And number two, if you tried to have a super predator, it would not get enough food. It would eat not only the lions, but it would also eat the zebras probably. And that's unstable. It's very likely that the super predator would go extinct. So we're competing within levels. We are consuming between levels. Okay, and notice that the way we've got this diagram, you have species 2 consuming these 2 plant species. Species 3 is consuming these 2 plant species, but hey, it's also competing with 2 for this one. So you can diagram competition here. You can make that very explicit if you need to. And species 1 here consumes the 2 herbivores, but look, it's also an omnivore. It's also consuming this species here. That's really an important thing. So let's talk about what makes food webs stable versus unstable. Okay, people think they know something about ecology often. And so in ecology, there's this common saying that everything is, who can finish the sentence? Everything is connected to, anybody? Everything is connected to everything else. No, that's exactly wrong. If that were the case, most species would go extinct almost immediately. Food webs are unstable if everything is connected to everything else. Species go extinct when that happens. Here's something that is stable. Notice that you don't have everything connected to everything else in this food web. You have a compartment here. these species are connected to this one. These species are connected to this one. Often the reason for that is that although these four species make their living in a common way, they may not directly compete with each other. And they may have very different lifestyles, and they may be eaten by different consumers. We would call this a guild. What's an example of a guild? These might be trees. These might be grasses. Okay, they compete to some extent with each other, but they don't compete strongly, very directly. They're mostly competing with others like them. Grasses are mostly competing with other grasses. Trees are mostly competing with other trees. There are not that many animals that eat both trees and grasses. And so you have consumers that specialize on trees and consumers that specialize on grasses. Now, let's ask ourselves what happens if you lose this species. Well, it's hard to tell, maybe not much, because this species is still got a resource. And it's not sharing this resource with anybody else. So whatever happens here, if we lose this species, it will only have an effect on this one. And that limits the damage. Let's consider the opposite possibility where these two consumers eat all four of these species. So this one is eating all four. This one is eating all four. Well, now if you lose this one, these two are competing for that resource. And now you're affecting the competitive relationship between these two species. It's possible that if you lose one of these resources, somebody up here will gain an advantage over the other and drive the other extinct. Well, if that happens, then you're breaking the links between the trophic levels, and it's very likely that further damage will occur. For instance, if you lose this species and this one gains an advantage and can competitively exclude that one, well, look what happens. This one no longer has a predator. It's free to grow exponentially and is not controlled in any way. It can drive these two extinct, potentially, which would then cause the loss of that one, which would then cause the loss of the entire web. You'd greatly simplify the web. You'd lose most of the species in it. And in fact, what we find is that trophic organization is highly compartmentalized. These guilds are crucial for stability. If things are connected to everything else in the web, somebody's going to go extinct with any little perturbation. And you'll lose a substantial number of species. So the way to compare the stability of food webs is to count the number of species. In this case, we have 4, 7. And then to count the number of links. 1, 2, 3, 4, 5, 6. 6 links, 7 species. The higher the number of links per species, the less stable the web. If we had everybody connected to everybody else, then, at least with these two, then we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 links and 7 species. That's less stable than 6 links per 7 species. If this was an omnivore, let's make it the extreme case where it eats everything in the web, then you'd have the 10 links that you had, plus another 1, 2, 3, 4. You'd have 14 links. 14 links and only 7 species. That is incredibly unstable. That food web will crash very quickly, and species will go extinct. The lower the ratio of links to species, the more stable the food web. That counters the common understanding of ecology as something in which everything is connected to everything else. Yes, there are lots of connections among species, but no, things are not connected to everything else. Yes, there can be unintended consequences of manipulating a food web, but that damage is limited more than you might expect, because in nature, unstable food webs don't last. The ones that we see are relatively stable. And so messing with the food web will damage it and will affect all the other species in it to some extent. But because it's a stable food web, mostly those changes are going to be small. Unless you're a human and you're doing something really stupid, which is generally how we find out about these things. Okay, so compartmentalization and the number of links per species is really important in understanding the stability of food webs. Having discrete compartments that are not connected to each other is like having extra legs on a chair. If you kick out one of the legs and saw it off, if you have 4 legs, you can still balance on 3. If you have 3 legs, harder to balance on 2, but you can do it. If you have 1 leg and you saw it off, you're going down. The more compartments you have in a food web, the more stable it is. The fewer connections per species you have, the more stable it is. Okay, questions about that? Okay, we'll talk about the number of trophic levels in just a second. But first, let's talk about omnivory and try to explain why omnivory is destabilizing. Okay, so here's that little food web we saw earlier. And here's an actual food web that we just took out all the information and just showed you the ball and stick diagram. And so this has 5 trophic levels, and you see that you have a resource species down here. You have a primary consumer. That's so far so good. And now you have a secondary consumer that eats that species, but is also eaten by a tertiary consumer. And what's more, the tertiary consumer eats this species, and it also eats the resources of that species. That's why omnivory is unstable. Think about those predator-prey cycles, right? Think about a predator and its prey, right? They're in kind of lockstep, following like this. Okay, well, let's draw that on the board for just a second to illustrate. Okay, so this is the predator, this is the prey, this is time, this is numbers. Now, look what's going on with the prey, right? The predator's consuming it and driving its numbers down. And at some point, it kind of bottoms out. Okay, why is it able to rebound? Why is it able to go back up? Because what's happening to the predators at that point? They're decreasing. So predation pressure is decreasing as prey numbers drop. So the prey are getting a break because the number of predators is dropping. if the predator can also eat the food of this prey item, two things happen. Number one, the number of predators doesn't drop. The number of predators stays high. So instead of predator numbers dropping and lowering the predation pressure on the prey, they stay high, they continue to drive the prey down, they drive the prey to extinction. The other problem, of course, is that if the predator is eating the food of the prey, how are the prey going to get enough resources to build their population back up? There's nothing for them to eat. There's no resources for them to rebound. So for two reasons, omnivores destabilize food webs. What is very likely to happen in a case like this is that this species will go extinct and this food web will collapse. Okay, and you see that we have that situation not once but twice. So this is an incredibly unstable organization here. This species this species here is eating the food of this one and it's eating that one. That means the pressure on this one is unrelenting and this species will likely go extinct due to a lack of food and continual predation. Unfortunately, what that then means is that this species is also likely to go extinct because this species is doing exactly the same thing. Now, despite that fact, we do sometimes see food webs with omnivory. And here are a couple of examples. So here's a very simple marine food web. This is a food web from the benthos of, I forget what ocean. But you have snails that eat stuff, and then down at the bottom you have clams and worms. Well, you'll notice that one of these predatory snails eats some of these shellfish here, and they eat the clams and the worms. So it's not impossible for us to have food webs with omnivory. They're just kind of unstable. This is an actual food web that's been very simplified. And this is a second food web, and this is a parasitoid food web. And this is really common in parasitoids. This is the exception about omnivory being destabilizing. When you have parasitoids, they can persist. And let's explain what's going on here. So you have a plant, you have a midge, which is a little fly that kind of stings the plant, makes it produce what we call a gall, which is a little ball of irritated tissue, lays an egg in there. And then the egg of the midge consumes that tissue and then hatches out into a fly. Okay, well, you have parasitoids of that midge. Here you have two competitors. They're competing to eat the midge. So what they're doing is they are cruising the plants, they're looking for galls, and then they are trying to lay eggs inside the gall to try to get at the midge that's in there. They're trying to lay a parasite in the midge, which will consume that larva. So they compete for that. Problem is that you have what we call hyperparasitoids. That's what these guys are. These are hyperparasitoids. They're not looking for the midge. they're looking for the larvae of these parasitoids. They want to lay their eggs in the larvae of the parasitoid that's eating the midge. So if these species find a plant that has galls with midge larvae in it, they ignore it. On the other hand, if they find a plant that has a gall, that has a midge in it, and they detect the chemical signature that one of these two species has laid an egg in that midge, they'll stick their ovipositor inside the gall, sort of feel around with this flexible needle, and they'll lay an egg inside the midge that will then find and consume the parasitoid larva. Okay, after it does that, well, geez, it's got lunch on a platter there. It's got the midge. So they just go ahead and eat the midge too. So that's how that works. So this is these are parasitoids. These are hyperparasitoids. And what would we call these things? If these are hyperparasitoids, what are those? Hyperparasitoids. Yes, we actually use that term. Yeah. So these guys are cruising not for the midge, they're not cruising for the parasitoids, they're cruising for the hyperparasitoids. But if they find a hyperparasitoid, it's inside a parasitoid, so why don't you just eat the whole thing? And then you can eat the midge. So that's how that works. That's how that food web doesn't collapse. Basically, the fact that these guys are eating the resources of the species below is kind of a side benefit. It's the potato salad at Thanksgiving dinner. The turkey is the parasitoid. The midge is left over. It's the potato salad. Or maybe it's the pumpkin pie. Whatever you want to call it. Okay. So we've talked about the organization of food webs in a couple of ways. They need compartments, they need limited connections, and it's better if they have less omnivory. If they have omnivory, they're going to be less stable. Okay. We will get to the number of trophic levels in a little bit. We may not get to that today. Now, there are certain species in food webs that are really, really important for the stability of the food web. Okay, we call those keystone species. Okay, and here's a keystone. That's a Roman keystone in a Roman arch. And of course, what a keystone does is distribute the downward force of gravity to the side. And it transmits the downward force of gravity to the side and then through these side columns so that the arch is stable. But if you remove the keystone, gravity takes the entire arch down. So this is a really apt analogy because keystone species stabilize entire food webs. And if you remove the keystone species, the entire food web will collapse. Now, it's important to understand the distinction between a keystone species, a dominant species, and an indicator species. Remember what an indicator species is? It's simply kind of the flag at Jazz Fest that lets you find your friends. It doesn't have any special significance. It's just a species that helps us refer to a community in a way that we all understand what we're talking about. And it's generally an obvious species. Okay, but a dominant species typically has large biomass. So a dominant species is often also an indicator species, but not always. A keystone species, however, can be very inconspicuous. It's not a dominant species, and it's often not a keystone species. It's often not an indicator species. Keystone species have a big effect on community stability despite having a relatively small biomass. So that's what this is trying to show you here. So these species here have a relatively low biomass, but they have an outsized effect on the community. Well, dominant species have a big effect on the community, but that's just because there's a lot of them, right? They provide resources for a lot of other species. Keystone species do something different. They organize interactions. Dominant species just provide a lot of energy, typically, for other species to eat. Keystone species organize interactions among other species. They are often top predators. So let's examine two food webs and show you how the keystone species in these food webs, as a top predator, prevents the food web from collapsing. Okay, and remember I told you that we often emphasize the exploitation interactions among levels. In this case, we're going to refer to competition within a level, because that's what the keystone species is organizing. So here you see a starfish, and this is the coast of Washington state. This is Baja California, and it's a more complex food web because there's a bunch more species. But the same thing is going on, exactly the same thing. So here you have all these species that are competing for space on rocky shores. So they all want to anchor themselves to the rocks, and they're all competing for that opportunity. And you have some species here that consume them. All right, well, here's a snail that preys on some of them, and here's a starfish that pretty much preys on everybody. Now, what's the significance of this starfish? You remember that experiment about Balanus and Thamellus on the rocky shores where we looked at competitive exclusion? Very same guy did this experiment. Did both of these experiments, actually. His name is Joe Connell, and he's like 90 years old now, and he's still teaching at UC Santa Barbara. God bless him. Still got graduate students. I wouldn't have graduate students at 90 if he paid me. But here's what he did. He did a modification of that very same experiment where he removed Balanus or removed Thamellus. But in this case, he removed the starfish. And he asked, what's the result of removing that starfish? When you take predation away, what happens to the food web? As it turns out, almost all the species went extinct. Why did they all go extinct? Because Piesaster, which is the starfish, is what we call a frequency-dependent predator. Remember when we had those predation graphs and the ratio-dependent predator could hit the y-axis, and that meant that it had another species? Had another prey species? Remember that? Well, Piesaster can eat any of these species. And it eats the one that's the most common. So whichever of these species is the most common one is the one that gets preferentially eaten by the top predator. So how do you get to be the most common one here? You're the best competitor. So if there's a competitive imbalance at this trophic level, and one of these species is a better competitor than the other one, it will grow and drive the others extinct unless the top predator eats it. And that's exactly what it's doing. Piesaster, the top predator, is preventing competitive exclusion at the base of the food web. So whichever of these species becomes the most successful, that's the one that Pisaster starts eating. It's a frequency-dependent predator. So if you take Pisaster away, whichever of these species is the most successful will then have a free run at driving everybody else extinct and just taking over. And that's exactly what happened. The entire food web collapsed when Pisaster was removed. You only had 2 of these left after removing Pisaster. So you dropped from 7 to 2. A wave of extinction caused the food web to collapse. It was even more dramatic in the Gulf of California, where a different starfish, Heliaster, was the top predator. It was also frequency dependent. Look at what it's eating. It's eating these guys, it's eating these guys, and these guys. So it's eating 4 of the 6 down here. When you remove Heliaster, a couple of these get an advantage and competitively exclude the others. So everybody here goes extinct. That means that the food for all these intermediate levels disappears. And you drop from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You drop from 13 to 4. That's all that's left. The food web collapses, most of the species go extinct. That is a keystone species. It prevents the collapse of the web in the same way that a keystone prevents the collapse of an arch. Okay? So here's another couple of examples, this time not so diagrammatic. But here we've got keystone species. It's again a starfish. We use a lot of these intertidal systems because they're just dead easy to manipulate. You just pick up the starfish and throw it out of the enclosure. But here is the number of species that we had in a food web before you remove the starfish. It's 15. After you remove the starfish, it drops to 8. Okay. Here's a second study in which you had 20 species, and that drops to 14 after you remove the starfish. So this is actually really common. There are many kinds of keystone species. Not all of them are top predators. Beavers are keystone species in wetlands in North America for a very different reason. They provide ponds that would otherwise not exist. You take away the beavers, all the pond-dwelling species go extinct. Elephants are keystone species in the savannas of East Africa because they knock down trees, they consume trees, and they open up opportunities for grass. If you take away the elephants, the grasslands succeed into forest, and all the grassland species go extinct. Okay, but it is really noticeable and really common for keystone species to be top predators. Now, there are different kinds of food webs that we use for different things. So let's finish today by talking about the uses of food webs and how we conceptually make use of this technique in ecology to understand these relationships. So we distinguish like 3 types. First, there's just a connectedness web. That's generally just who eats who. And so here's, again, another intertidal web because it's simple. That's really simple, right? Yeah, that's really simple. But it shows you who is eating who. These are the primary producers. These are all algae and photosynthesizers. And these are the primary consumers that eat them. So you can see that, say, Catharina, which is a snail, eats 1, 2, 3, 4, 5 of the members of this community. Terrific. And you can see that Alaria, which is a little alga, is eaten by Catharina, by Strongylocentris, a different snail, and by Acmea, a third snail. Great. So we are specifying who eats who. But that's all we're specifying. We don't specify anything about the relative importance of this stuff. A second way that we can use food webs is to ask about energy transfer. So this is an energy flow web. In an energy flow web, we eliminate all of the connections in which there's not a lot of energy being transferred from one species to another. So look, Alaria is consumed by Catharina, Strongylocentrus, and Acmea, but mostly it's Catharina. Catharina is getting almost all the energy out of this. These two are not getting a lot. The thickness of the arrow is proportional to the amount of energy that these consumers are getting from a particular resource. So it can cut two ways. You can see that Corallina mostly is consumed by Acmea. Mitra is consumed less by Tonicella and only a little bit by Catharina. And you can also see that Acmea mitra gets most of its energy from Corallina and a little bit from Lithothamnium. And although there's a connection here, it does eat this, it's getting hardly any energy from it at all. We can just ignore that. So if we're interested in energy flow, as we will be when we talk about ecosystems, this is the kind of food web that we might use. If we want to understand the keystone species, that's what we call a functional web. We ignore everything in the web except the relationships that maintain the diversity, that prevent the food web from collapsing altogether. So we find that there are exactly 4 relationships that maintain the diversity of this web. The only way you can do this is by selectively removing species. So this kind of web requires an experiment. It requires removing species one by one to identify the keystones. So this is one keystone relationship, and it's perhaps the strongest one in the entire web. If you remove Catharina, benthic diatoms kind of start monopolizing photosynthesis here, reducing opportunities for these other guys, and some of them will start going extinct, which means that some of these guys will start going extinct. There is a somewhat less strong relationship between Hedophyllum and Catharina. And the point is that this just looks at who eats who, regardless of how much they're eating. This specifies how much is being eaten, and this must be determined by experiments. That's the only way. Okay? All right. We'll have a little bit to say about trophic cascades next time, and then we'll talk about succession.